Results. I think some of you actually did better on this quiz, but more of you didn't do as well on this quiz, so that's why the average went down. So I was wondering, if if you think that we need to, like either I or Peng needs to hold an additional weekly office hour, or maybe I should hold a review session. I mean, it's not it's not too late. I mean, of course, I'm going to not count your lowest quiz grade. Okay, so if you did really poorly on any quiz, you don't have to worry about it that much. But it'd be nice to just sort of catch up before we have too much more material covered. So maybe just show of hands, like how many people think that we should have an additional weekly office hour? One, okay. Maybe those of you who think so, maybe if you can send me suggestions for time slots, because I know you're all busy with classes and so on. So any suggested time slot that would be convenient, I'll happily consider. Okay, review session. Before we get too much further, I'm happy to give a review session, but how many? Okay, great. Okay, so maybe we'll have some refreshments or something like that. Okay, so I'll look at what time. Is it late in the day is good, or like a lunch hour, or I don't know what? Right after this class? That's convenient for me, but. Well, this is social hour on Tuesdays, but I'm happy to stay like right after class on Thursday. Is that convenient? No? Prefer like a lunch hour before? You have class right after. Nighttime? Nighttime? Nighttime. Yeah, actually, so I don't want to show you my calendar because it's crazy, but next Wednesday, I actually happen to be staying here, I mean, for dinner at 6:30, so with the chancellor, so I have to stay around anyway. Let's see, so that's at 6:30 at the faculty club. So would next Wednesday, like from 5 to 6, would that be convenient? Or 5:30, huh? Well, what? Yeah, I know in the past, the previous chancellor would always invite us to his home, but I don't know. I guess this new one wants to meet us in the faculty club. But anyway, yeah, so it would next Wednesday evening, like 5, I don't know, what time do you eat dinner? 6? Okay, so 5 o'clock next Wednesday would be convenient? Okay, so I'll try to reserve a room for 5 o'clock next Wednesday. Okay, thanks. Okay, so the question is, how would the review session be different? Yeah, so maybe I would try to go over the most commonly missed concepts on the first two quizzes, basically review. So basically it's like for those of you who haven't, I mean, might have missed some basic things in the first two. No, I wasn't planning to review for the upcoming quiz, but I'm happy to answer any questions, of course. Yeah, but I was thinking more to review the things that a lot of people missed on the first two quizzes. Is that? Can it be webcast? Actually, yes, it can. I mean, I would have to post it separately on the class website. It wouldn't be part of edX. I mean, not edX, the ETS service webcast. But I can do that because on this laptop we have the software to capture locally. Yeah. Okay. All right, great. Any other suggestions for making sure you don't all? I mean, we want to make sure you catch up. Okay, you have. Feel free to ask a question about something else.
This is about narrow banding.
Narrow band?
You have one side that's narrow.
Okay, so your question is about like degenerate doping and how that narrows the band gap? Narrow base. Oh, okay. All right, so so the question is, okay, so when I talk of, the homework that was just turned in, right, okay. So narrow base refers to one or both sides being shorter, much shorter than the diffusion length. One or both? Yes.
So it's not strictly both.
It's not strictly both. Yeah, sorry. Okay. So that was confusing for the homework. Did you like? Okay.
I said it was like half. I said it was
Yeah, narrow base on one side. Yes, yes, right. So the homework that you just turned in had to do with, okay, so, ordinarily in a transistor you have, I think I had the PMOS transistor, but anyway, you have usually the more heavily doped side is usually very short compared to the more lightly doped side. So that's more realistic. So this is for an N-channel MOS transistor. And I think for the homework that you just turned in, it's the opposite case. So it's a P-channel transistor. Right? So the point is that you can have, okay, so narrow base has nothing to do with one-sided. I mean, you can have, these are both one, in each case, one-sided junctions. One side is much more heavily doped than the other. So one side generally will contribute more carrier flow across the junction than the other. But it's independent of which side is short or long. Right? So you should, in principle, be able to draw, the current density profiles. Let's see. So here's minus xp, xn. So this is the n side, p side. You should be able to cover all cases. Okay, let's see. So if I went like this and drew this for j sub p, and oh, it has to add up, right? Okay. So if I drew this for, and you should be able to tell me if it's a one-sided junction, which side is more heavily doped, and if it's a short base diode, which side is short. Does that make sense? Okay, so let's see, which one to go first? Okay, so how can you tell if this is a one-sided junction? Well, no. Okay, so somebody asked, said something about the decay. So one-sided means that one side is much more heavily doped than the other. So here, this is maybe moderately one-sided. So here, J sub p, the hole current crossing the junction, the depletion region, is significantly higher than the electron current. Okay, so electrons are flowing this way, holes this way. So this is so clear. Hopefully you can see. Well, usually what this means is that the p side is more heavily doped than the n side. So that means the concentration gradient is greater for holes than electrons, so you have more diffusion current due to holes. Okay. Now, the fact that the current decays means that the excess carrier concentration is decaying on the n side. It's not decaying on the p side, and that's because you're not losing any. Okay, so on the minority carriers on the p side, you're not losing the diffusion current because they're not recombining, right? They're not dying out in the p region as they travel towards the contact. So in this case, which side is short? P side, right? The n side is long, so there's plenty of room for the carriers to die out due to recombination. In other words, what is it? The mean, not the mean free path. Diffusion length. Yes, the diffusion length is rather short compared to the length of the n side. Okay, so you should either be able to tell me, or you should be able to draw this kind of a diagram if I, specify a diode to you. Okay, sorry, James.
So, I guess I have two questions.
Oh, so this figure here, actually this figure here is intended to be linear, right? Otherwise, it wouldn't be a exponentially decaying function here. If I drew it on a log scale, it would be straight lines.
Yeah, but also the JP and JN.
Oh, that's true. Okay, well, this is intended to be, okay, so I'll specify linear. But yeah, this simple plot is to show, is intended to be a linear scale. But yes, if one side is doped like 100 times more heavily than the other, then yeah, so JP might be way up here and JN down there. Yes, you're right. Yeah. So yeah, so this is not the same as yeah, that case up there. That's right. Yes. For a p-n junction? You mean just a normal p-n junction? What would it look like? Okay, so okay. So just to be clear, this one is, so this is this case, right? Okay, so the question is, what would it look like for an ordinary p-n junction, like not one-sided? Yeah, what I just drew down here, I think, well, except for the fact that James pointed out, it really, I should have exaggerated. If it's 100 times more heavily doped on the p side than the n side, then pretty much you'd probably get maybe 100 times more current crossing, I mean, holes crossing compared to electron current crossing. Now, I say maybe only because if the p side is very short, which is what your homework problem was, see, if the p side is really short, then that can actually increase the magnitude of the electron diffusion current because, okay, so let's write this down. Let's write, so I naught for this particular diode is, okay, so we have QA Ni squared. Okay, so we have diffusion, let's do the first term. Diffusion of holes across the junction, so that's d sub p. And then we have the holes dying out on the n side, so that's according to diffusion length, L sub p, and the dopant concentration on the n side, right? But then now you have d sub n over, so this is now W sub p. Let's call it W sub p prime, right? Because it's short on that side. So the concentration gradient relevant for the electrons is dictated by the length of that short p side. So that's why you have WP prime here. And you have n sub a on the bottom. So I guess my point was that even though n sub a is orders of magnitude, let's say 100 times greater than n sub d, that doesn't necessarily mean that this term is 100 times greater than this term, because it depends on, you know, LP and WP as well. So LP is typically, you know, 10 microns or on the order of 10 microns. WP, tenths of microns. So that's why it might not be a factor of 100 difference here, but it will typically be like 10. On the homework, I think it was more like even less than 10, factor of 10 difference. Okay, so did you still want me to? No. Okay, all right. That's good. Any other questions? Yes. Yeah, so in this class, if I say it's short base, you can just assume there's no decay. But in reality, yes, if there's a little bit of recombination of minority carriers before they reach the metal contact, then yeah, there will be a slight dip. And that's why you have this hyperbolic cosine, you know, or hyperbolic sign for the current. Right? So it's just, it looks kind of straight, but it's a little bit dipped, right? Because you're losing some carriers to recombination. Well, that's good, because you'll need to know this for the next quiz, actually. Good questions. Okay, so today we're going to look at diodes further, because diodes are actually, do you remember any applications for diodes that you covered in like the equivalent to EE40 or EE100, whichever class you took? DC converters. So how, okay, so a DC converter. So you convert like an AC signal to a DC, right? So AC voltage that is positive and negative, and then you output a fairly constant positive voltage, right? That's right. So that's a really good example of how a diode is used. Okay. Is that like with a Wheatstone bridge kind of a? Yeah. Okay. So I haven't. Do you want to draw that? No. Okay, let me see. So it's something like this, and I actually didn't review this, but it should be, you should probably be able to correct me if I get it wrong. All right, so a couple of diodes are designed to make current flow through a resistor in one direction. Is that right? And then another couple of diodes are designed to have current flow through the same resistor in the same direction, but with different polarity of voltage. Done it in two different colors. Let's do that. Okay, so like, oops, how do I do this? So these two diodes, let's say, are going to be on if the voltage applied is positive down here and negative up there. Whereas the red diodes turn on if you have the opposite polarity of voltage applied. So here's your your power supply, like AC. And then the voltage across this resistor is always going to, the current is always going to flow in only one direction. So the voltage across that resistor is going to be only like one polarity, right? Okay, so this is a simple example of how diodes could be used in a circuit. So the key point here is that the diodes sometimes, so if you have an AC signal, like going positive and negative as a function of time, let's say this is the VAC, sometimes those diodes are going to be on, sometimes they're going to be off, right? So let's say roughly half the time the diode is on when the appropriate polarity of voltage is being input. So what's important to understand is not only how the current versus the applied voltage looks like for a diode, but also how a diode can actually turn on and turn off. Because actually it cannot turn on and off instantaneously. It takes some time. There's going to be some delay. So that's basically what we're going to cover today in class. Okay? Now to understand why it takes some time for a diode to turn fully on or to turn fully off, we need to just sort of review this concept that charge is stored in the diode when in the steady state. Okay? So when a diode is on, let's just say forward biased, let's just look at the P side. Here's the P side. Let's say this is a long base diode. Let's plot the excess minority carrier concentration on the P side as a function of distance. It's going to look something like that, right? And the value at the edge of the depletion region is going to be the equilibrium value, but it's going to, this is the excess carrier concentration. So it's going to be enhanced by QVA over KT. You have this minus 1. Minus 1 is there just because we're plotting the excess minority carrier concentration. Okay? So in steady state, this is what the minority carrier profile looks like in the quasi-neutral P region. So we actually, in a sense, are storing minority carrier charge in the quasi-neutral region. And the same thing happens on the N side. If we plot the excess hole concentration on the N side, and it's going to look like an exponentially decaying function. And at the edge of the depletion region, you have the equilibrium value enhanced by the same factor as for the minority carriers on the other side. Okay? So these equations on this slide simply derive a simple formula for the amount of charge, minority carrier charge stored, or excess minority carrier charge stored in the quasi-neutral regions. Okay, so if you take the integral of an exponential function, it turns out, and then so you integrate over the entire quasi-neutral region. It turns out it's pretty easy to remember. All you have to remember is that, okay, that's going to be proportional to the area, and it's going to have some charge. Okay, so electrons on the P side have minus Q charge each, and you just multiply the density of electrons times the volume. Okay, well, average volume. So that's the cross-sectional area times the diffusion length. Okay, so this is the carrier concentration at the edge of the depletion region, and then times the diffusion length. Right, so hopefully that formula is not too hard to remember. Right, it's just the concentration, excess concentration at the edge multiplied by this volume, and the length effectively is the diffusion length. And remember that electrons are negatively charged. And we can do the same thing on the N side for the minority carrier holes. Okay, so excess carrier concentration, minority carrier concentration at the edge of the depletion region times the diffusion length of holes on the N side. And then holes are positively charged, so Q, there's no negative sign there. Okay, so if we change the voltage applied to this diode, then we have to change the amount of charge, the minority carrier charge, excess minority carrier charge stored in the quasi-neutral regions, right? Because of this because of this VA dependence. Yes, question? Okay, so the question is this formula an approximation? I don't think so. I mean, it's an approximation to think that any diode quasi-neutral region is infinitely long, but I think this is an exact formula. Because you evaluate it at, okay, infinity on either end. Yeah, so, okay, so I think the qualitatively what you're saying is that, so the question is, so if I actually drew, I mean, so this, what this equation says is that it's kind of like all of this charge underneath the green curve is going to be equal to the charge, let's say if we just somehow had a constant concentration and it ended at L sub n. It turns out that apparently that's the case. Yeah, it is the case. Okay. Okay, so let's derive the so-called charge control model. So in the charge control model, we start with the minority carrier diffusion equation again, because now the minority carrier diffusion equation talks about what happens when something's changing with time, right? So what we're getting at is coming up with a model that will allow us to qualitatively understand how a diode turns on and off. So we have to start with some equation that shows something changing with time. Okay, so let's look at just the n side, and it will have a similar derivation for the p side. Okay, so on the n side, holes are minority carriers, and we have this minority carrier diffusion equation that we sort of derived in the past. Okay, so remember, what the minority carrier diffusion equation just says, okay, the change in the number of excess holes is going to be equal to, at any location, it's going to be equal to the change in current. But remember, since it's a minority carrier that we're worried about here, the drift current we're ignoring because the drift current is negligible compared to the diffusion current for a minority carrier because the minority carrier concentration is so low. So we take the derivative of the diffusion current, and that's how we get the second derivative of the excess carrier concentration. Then the concentration of carriers can change if there's some net recombination or generation going on. Okay, so that's just a reminder of where the minority carrier diffusion equation comes from. So we're actually going backwards. I think this is the way it's done in the textbook period. So now we're going backwards, saying, okay, well let's just call that. Let's write that first term on the right-hand side. Let's write it in terms of current density. Okay, so remember that current density is going to be proportional to the gradient in carrier concentration, and it's going to be proportional to the diffusivity. And for holes, I guess there's a negative sign there. So actually, we can just rewrite the minority carrier diffusion equation like this. So if you started from the minority carrier diffusion equation, you would have started with this equation, actually. Okay, anyway. Does anybody have any questions qualitatively about what this equation means? All right, so here's just a little bit of math, calculus. So we basically integrate every single one of those terms over the entire quasi-neutral n region. So that is from xn, from the edge of the depletion region, to infinity. And we note that at infinity, the whole current density should be 0. It should have died out. Okay? And if we're multiplying by area, then that's just going to give us the current I. All right? Okay. So what does this equation actually tell us? Okay, so notice this was on the first slide. This is Q sub P, right? That's the stuff in the expression in the brackets is just equal to the total excess minority charge carrier concentration in the quasi-neutral region. Okay, So that's how we end up with this equation at the bottom of the screen. Okay, so in steady state, when nothing is changing with time, that means the change in the total charge stored is 0. Okay, so let's draw a fluid analogy just to help you understand this equation. So let's say that the quasi-neutral region represented by this beaker, a beaker. Okay, so that's the, and let's say that we have a faucet. I can't draw very well, so that's flowing water into this beaker. Okay, so the amount of water in this beaker represents the total charge stored in the excess minority charge stored in the quasi-neutral region. Okay, so this represents holes diffusing into the quasi-neutral region at x sub n, right? Maybe we should show more holes. And let's say there's a hole in this beaker so that you're losing some holes with time. So this would be loss due to recombination. That's what this equation pretty much states, is that if the amount of holes in the quasi-neutral region is changing with time, then the rate at which it's changing with time is going to be equal to the difference between the rate at which you're adding holes and the rate at which you're losing holes. That's it. Okay? Okay, so what we did in lecture 10 was we derived an expression for the current flowing in a p-n junction one way. Okay. So today we're going to very quickly come up with a much faster way to arrive at the same equation for the current in a diode. Okay, so the current versus voltage equation is describing a steady state. So we set that equation to 0. And that gives us a simple expression that the rate at which holes are flowing, or current is flowing due to holes diffusing through the n region, is just equal to qp over tau p. That's pretty much it. Okay. And similarly, we can do the same. We can go through the same exact derivation that the current due to electrons diffusing across into the p region, so entering the p region at minus xp. It's just going to be equal to the total charge, excess minority carrier charge stored there, divided by tau sub n. So the total current flowing in the diode is equal to I sub p plus I sub n. Okay, so let's see. So the total diode current is due to holes flowing in at xn plus electrons flowing. Holes flowing into the n side at xn plus electrons, the current due to electrons flowing into the p side at minus xn. Okay, so this is equal to q over tau sub p. This is minus q sub n tau sub n. And it's minus q sub n because electrons are negatively charged. Okay, so if you actually look at the equation, or let me just go back. For q sub p and q sub n, oops, oh, my finger does something too. All right, hopefully that's not too hard to believe. Right, because here, this term here, for example, is what this term is, right? So hopefully you can sort of see and this right here is, ni squared over n, na, right? Hopefully you see, okay, that we end up with the same ideal diode equation. Okay, so this is another simple way to think about how current flows in a diode, even in the forward bias state. Okay, so we were talking about narrow base. So how is this going to be different for a narrow base diode? Okay, so tau sub p and tau sub n represent the average time it takes before you lose in a hole or you lose an electron due to recombination. But in a short base diode, if a side is short, you don't lose it due to recombination. It actually leaves the quasi-neutral region before it recombines. So basically instead of putting tau sub n or tau sub p, if it's a short base, then you have to replace the tau by the transit time, tau sub tr. So this is a new parameter here that we would give to you, or you can calculate. But basically, bottom line is the current is equal to the total charge divided by the average time that the minority carrier spends in the quasi-neutral region. So it's either the time it takes to die out or the time it takes to move across and leave the quasi-neutral region. Okay? So if you actually, now for a short base diode, it's just a linear, rather than an exponentially decaying function, it's just a linearly, it's like a linear function going from the same value. So you have the value at the edge of the depletion region doesn't change, but now it goes to 0. If you have a short base, it goes to 0, in a short period, short distance. So this is like WP prime, right? Okay, so rather than having an exponentially decaying excess carrier profile, it will be linearly going to 0. And so you can integrate that. So it's just 1/2 times the height times the width. It's just a triangle, right? Okay, so you have a simple formula then for the total excess minority carrier charge stored in the quasi-neutral region. And you can calculate the current. It's just a diffusion. You can calculate the concentration gradient. It's just a linear function. And you end up with this expression. So if you set, you set this to equal to QP over the transit time, right? Then you find out that the transit time for holes is given by this equation. So it's the width of the quasi-neutral region squared over 2 times the diffusivity. Okay, so qualitatively, again, it makes sense, right, that the higher the diffusivity, the faster carriers would diffuse through the quasi-neutral region, so it should spend less time in the quasi-neutral region. So the transit time is inversely proportional to the diffusion constant. Okay, so what about the width of the depletion, of the quasi-neutral region? It's proportional to that squared. Okay, so can somebody explain why it would be quadratically dependent, more strongly dependent on the width of the quasi-neutral region? All right, well, maybe think about it. You guys can chat if you want. I mean, it's fine. Okay, I have a gadget I'm going to give out. I thought I had a gadget. We have a handy dandy tool here. The question is, why is it square? All right, James, first shot. Wait, the fusion length is square root of dt. There's no 2 there. I'm not looking for a factor of 2.
No, but I mean, that is basically the diffusion equation.
So you're saying the diffusion length is equal to the square root of dt. Okay.
Well, yeah, I mean, in the actual, that's generally the assumed
Okay, but
so when you find L, replace it with W, you get a square to find time.
what?
No, your diffusion length.
Oh, I see. Oh, what? Does that work? Okay, so let's see. LP squared equals dp. Okay, so you're saying, okay, and then tau p, that's the reason? Oh my goodness, that's math. I don't want equations. Okay, I'm not going to give you this. I'm going to give you this. No math, no equations, no equations. Okay, intuitive, qualitative explanation. That was a good. That was good though. Math, if you, yeah. All right, no equations. Yes, Peter.
Can you also say that, so once the longer, okay, obviously it takes longer to reach the PM, but also the fact that
I think you're saying it right, but it's not super clear. So let's see. Does somebody else want to take a? Don't. Okay. Louis is saying no. Don't give it to him. Okay. So I'm going to draw this. I think it's like WN prime, right? Okay. So here's the whatever. So if WN prime gets shallower, I mean it is shorter. Okay. I'm going to give one more chance. Andrew. This is a handy dandy tool. Okay. So I have to tell you. So actually, so a week or two ago, Applied Materials and Tokyo Electron, they're the biggest semiconductor equipment manufacturing companies that they decided to merge. But last year, actually, another two top equipment companies merged, and that was Lam Research and Novellus Systems. So this is a little screwdriver kit from Lam Research, basically. And I've never had to use it, so I'm going to. Okay, so Andrew.
so I was thinking, okay, so if you shorten WN, there are two things that.
Yep. So you don't have to travel as far.
The second contribution is your speed to do with the diffusion.
Slope also. So it's not only that you go through a shorter distance, but you go faster because the gradient is steeper. That's the correct answer. All right. Good job. Okay. So that's it. So same thing on the P side. The transit time, if the P side is short, is going to just depend quadratically on the width of the quasi-neutral P region. Okay? All right. So just to summarize then, the charge control model just states that, okay, you're going to store a bunch of excess minority carrier charge in the quasi-neutral regions of the diode, and that's exponentially dependent on the applied bias. And then depending if it's short or long, you have to just multiply it by the diffusion length, okay? Or if it's short, you multiply by the width of the quasi-neutral region. So hopefully it's not too hard to remember these equations, okay? Okay, so let's see what happens. What? Oh, okay, so this is kind of like review. All right, so this is like, this is basically deriving the ideal diode equations, okay? So long base, short base. If you have, okay, the very first example we went through at the beginning of this lecture, we had a short P plus and a long N diode. What would the equation be? Still going to be equal to minus. Actually, it's the same. It's the same, except you have to use WP prime for the tau on the P side, and then so that's for electrons on the P side, and you have to use the recombination lifetime for the holes on the N side. Okay. All right. Questions on the ideal diode equation from the view of the charge control model? Okay, we're going to, okay, so one way that the bias is changed on a diode is by applying a small signal. So let's say you have a diode and you want to flow current through it, so you can have some, let's say a battery or something, a power supply, VA, okay? but then you apply I'm running out of room here, a small signal, little v sub a, on top of that. So in addition to some DC bias voltage, you're just going to vary the applied bias a little bit around it. So on a current versus voltage plot, it's going to look something like this. But let's say you're going to operate it here, okay, and then on top of that, you're applying some voltage, a little bit of voltage on top of that DC bias. So you're moving up and down this IV curve. So the current is going to change by this much, by this much for this much change in voltage, right? So here's little VA, and so the question is, what is the resulting AC current change or AC current signal that results from that small voltage signal? So this is why we call it a small signal model. We're only looking at small changes in the voltage and the current. So this is, okay, this is little I, right? So little I just means it's the change in current flowing through the diode when you change the applied bias. So VA is a small signal, right? So it's just a change in bias in the applied voltage. Okay, so if you want to use this in a circuit, if you want to change the voltage across the diode, then you have to know, okay, how much is the current going to change? So two components here. First of all, you can model the diode as a resistor, right? Okay, so when you change the voltage, you're changing the potential barrier height. So you're going to change the number of carriers that can diffuse across the barrier. But also, in order to change the voltage, what else do you need to change? Well, that's what we were talking about, the charge, right? The charge stored in the diode. So if you change the voltage, you have to change the excess carrier stored in the quasi-neutral regions. And you also change something else. You change the depletion width. Okay? So let's think about that qualitatively. You have a P and N region. So let's say if I want to increase, let's say I want to increase just by a little bit the applied bias, make it a little bit more positive. Okay, let's just say that this is ground. Okay, so what happens to the quasi-neutral, the charge stored in the quasi-neutral regions? Does it have to increase or decrease? I increase the applied bias. It has to increase, right? Okay, so you have to flow in. Okay, so this is positive. Okay, so you need to have holes flowing in, and those holes go across the junction, and they build up this profile of holes stored in the quasi-neutral N region. And then you have to flow in some electrons, which diffuse across the junction and build up more the charge stored on the P side. Okay, so that's to build up the quasi-neutral, the charge stored in the quasi-neutral regions. Okay, what happens to the depletion region? Does it grow, get bigger or smaller when you increase the forward bias? Smaller. And how do we add charge or take away charge to make it smaller? Okay, so on the P side, we want to make the region where you have negative acceptors, make that region less long. So you have to add holes. So again, you have to add holes sort of to cover up more of that negative acceptor charge to shrink the depletion region. Adding holes. Right, so when you change the voltage, you have to add some holes to shrink the depletion region. Does that make sense? So you have, okay, I'm just going to draw the depletion region here. So you have negative acceptors that are, because it's depleted of mobile carriers normally, so you have some certain width. And, okay, I'm just going to draw like this. So if you want to, so let's say this initially was the depletion width. If you want to shrink it, you have to add holes, right? So that the total charge, let's say here, is going to be P minus NA, right? And you can make it 0 if you add holes, right? So you want to add holes on the left to cover up some of the acceptor ion charge to shrink the depletion region. And same thing on the right. Similarly, on the right, you have to add electrons to cover up the positive, to cover up the positively charged donors. So to change the voltage applied to this diode, you actually have to not only have charge going in to change the amount of charge stored in the quasi-neutral regions, but you also have to have charge going in to change the depletion width. Okay, so for a change in voltage, you need to have a change in charge stored. That's capacitance. That's small signal capacitance, right? So basically, that's what this term represents. And this term just represents, okay, the change in current just due to this slope here. Okay, so if you change the voltage due to the slope here, you're going to change the current. Okay, so let's look at the resistor first. It's easier to look at this because we plot current versus voltage. It's just easier to look at the change in current for a change in voltage, right? The change in, so this is the DC IV curve. So the change in current for a change in voltage, you plug in the ideal diode equation, and then you can find that, okay, so this is under, so typically typically when we care about a small signal model, this is for strong, usually in strong forward bias mode. In other words, the diode is turned on and flowing a reasonable amount of current. So in that situation, sometimes for some circuits, then we add an AC signal on top of that. Okay, so under strong forward bias, this exponential term is much greater than 1, so we can sort of ignore it. I mean, approximately ignore it. So we get a simpler expression for the derivative of the current with respect to the voltage. Okay, but considering that, so that means I is approximately I naught e to the q VA over KT. Okay, so if you look at this expression here, that's here, right? So the definition of small signal conductance, which is defined to be 1 over this small signal resistance, it's just the change in is actually equal to this, right? This is defined to be the small signal conductance. Okay, so it's just IDC over KT over Q. Is that obvious? Did I skip a step? Oh yeah, right. When you take the derivative of this, right, it's KT. Isn't that right? KT. Yeah, it's KT over Q times IDC. Right. Oh, sorry. Okay, I need to get it right. So Q over KT times IDC. Right. Okay. Sorry. Thanks. Okay. So first of all, conductance is the inverse of resistance. Okay. Resistance is like ohms, so it's like volts over current. So here's volt. KT over Q has units of volts, and current has units of amps. So unit-wise, this makes sense, right? So conductance is just inverse of ohms, basically. Okay, so qualitatively, what this says is that, okay, so the conductance is defined to be the change in current for a given change in voltage. And if you go higher and higher up on this curve, you go higher and higher up on this curve, it gets steeper, right? Because it's an exponentially increasing function. So the conductance increases. The small signal conductance increases because the change in current for the same change in voltage, like the tiniest change in voltage, the change in current resulting from a small change in voltage will increase if you're operating at a larger bias point. So remember, the DC voltage applied is VA, and so the current corresponding to that DC voltage is IDC. Right? So if we're operating at a higher IDC, then the slope is steeper, so you get higher small signal conductance. Okay? So so the resistor there is, the value of that resistor tells you then how much change in current you're going to get for a given change in voltage. Okay, so that's due to diffusion across the junction. So now let's derive expressions for this small signal capacitance. Okay, so let's first sketch the excess minority carrier charges stored in the quasi-neutral region. I think it's just the same, nothing tricky here. Yeah. Okay, so we're assuming long base, goes to 0. And now let's just draw it. Let's say it's a symmetric p-n junction. Goes to 0. Okay, so this is q sub p, q sub n. Okay. How about the depletion region? Okay, so this is, you have excess carriers starting from the edge of the depletion region, but within the depletion region you have negatively charged acceptors and positively charged donors. Okay. So now if you change, let's see. I didn't leave myself much room. Oh, okay. Let me just draw this first. So if, let's say we started, well, okay, I'm just going to draw it. So let's say this is the electrons added to reduce xn, and this represents the holes, magnitude or number of holes added to reduce xp. Okay, so as I said before, so if we apply a additional small signal voltage that's positive, we have to shrink the depletion region so the depletion charge profile looks like this heavy black line. But let's say before we applied that small signal voltage, let's say the depletion region was out here, it was wider, so the charge density profile used to be spread out over a wider distance. So in order to shrink the depletion region, we had to add holes on the left and electrons on the right. Okay, that's all I'm saying there. Okay, so the black line is to indicate that little VA is greater than 0. The case when the applied AC voltage is greater than 0. Okay. So there's two components of capacitance here. So there's the depletion capacitance, which we sort of got a preview of, is similar to the depletion capacitance of the small signal capacitance of a Schottky contact, a metal semiconductor contact. Okay, so that's, again, because you have to change the charge at the edges of the depletion region when you change the voltage. Okay, so this is kind of like a parallel plate capacitor where you're adding charge, a little bit of charge on the P side, adding holes to the P side to shrink the depletion region on that side, adding electrons to the N side to shrink the depletion region on the N side. And they're being added at the edges of the depletion region, which have a width, a W. So basically, wherever you're adding and subtracting charge on either side, or adding plus and minus charge, those charges are separated by the depletion width. Right? So in essence, let's say this was the depletion width, so I'm exaggerating. This is the original depletion width, and we're adding electrons and holes to the edge of the depletion region width to shrink it a little bit. Okay? So that's why this is epsilon. So the permittivity of this material, of this dielectric, so-called dielectric material, is E sub s, and then there's an area of the junction, and you divide by the depletion width. Right? So this is the junction. Now we give it a subscript J for the junction capacitance. Okay? So that's a normal, that junction capacitance is always there. The diffusion capacitance is due to the minority carriers, the excess minority carriers in the quasi-neutral regions, which are diffusing through the quasi-neutral regions. That's why it's called diffusion capacitance. So that's why we have a subscript D. Okay? So if we change the applied bias by this little amount dVA, then we're going to have to change the amount of charge stored in the quasi-neutral regions on both sides. And the small signal diffusion capacitance this is defined to be the ratio of the change in charge to the change in voltage. Okay? So this is where the charge control model comes in handy, because now we know we have a nice expression for Q sub P in terms of I. Okay, so this is for a one-sided p-n junction. So let's say we only have to worry about like one of those terms. Remember, I is equal to q sub p over tau sub p minus q sub n over tau sub n. So for if the p side is much more heavily doped than the n side, we know that most of the current is due to hole diffusion and so on. Okay, so let's just look at this simple case. So you plug in q sub p is equal to tau p times I, and it makes it easier to take the derivative. Again, it's just the same as what we did to get the conductance. So you have a nice simple expression for the diffusion capacitance. Okay, this is again a small signal capacitance. So again, it's going to be proportional to the current, DC current, the bias, the current at which you're biased about which you're making the changes. Does that should hopefully make sense, because the higher the current, the higher the operating current, the more minority carrier charge you're storing, right? Exponentially more, because these values here are proportional to e to the QVA over KT, right? So if you're operating at a higher current, you're operating at exponentially higher excess carrier concentration in the quasi-neutral region. So any delta or any change in the charge stored is going to be exponentially larger. Okay, I think that's the diffusion capacitance. Right, so let's talk about this. So there's two. So the total junction capacitance, so these two capacitances are in parallel. What that means is you have to add them together. Okay, so when I mentioned this here, electrons have to go in to charge up to add charge on the quasi-neutral p side. Holes have to go in to add charge on the quasi-neutral n side. Same thing, you still have additional carriers coming in to change the depletion region with. So basically, those charges that you have to add to change the voltage you have to add together. So you have to add the two capacitances together, the diffusion capacitance and the junction capacitance. Okay? So this is just a recap of the equations there. So hopefully it's not surprising. This diffusion capacitance is exponentially dependent on voltage. And so at moderate to high forward bias, it's dominant. It's going to be much greater than the junction capacitance. Okay, the junction capacitance, how does that junction capacitance change with increasing forward bias? Does it increase or decrease? W decreases, so junction capacitance increases. So the thing is, but this is sort of inversely proportional to W, and this is like exponentially dependent on the voltage. So it's a stronger impact. I mean, the junction capacitance does not grow as quickly as the diffusion capacitance as you increase the forward bias. Okay, so under high forward bias, the dominant capacitance is diffusion capacitance. And then only at low forward bias or reverse bias, in the reverse bias, you don't have very much excess minority carrier charge stored. In fact, it's negative. So the dominant capacitance in reverse bias is really just the junction capacitance. Okay? Okay, so capacitance is not really something that usually is desired in an integrated circuit. Somebody want to explain why? I mean, just fundamentally. Why do we not like to have significant capacitance, let's say, in a transistor? Let's go. That was in a separate slide. Yeah, why is high capacitance not desirable? Yes. So the answer was that essentially two terminals that are supposed to be electrically not connected at high frequencies, if you have a high frequency signal, will look like they're connected because you essentially have too much current that you need to supply to change the voltage. So it looks more like a short circuit. Yeah. How about in a digital? So that's kind of like an AC amplifier kind of application. Or how about in a digital circuit application where you're trying to pass high voltages and low voltages through some logic gates? Yeah, the rise time. Right, so if you need to have more charge added to your junction in order to change the voltage, then it's going to take you longer. I mean, assuming that there's the transistor can conduct when it's on, only a limited amount of current. It'll take longer to charge up your voltage, the output of your logic gate to high, or discharge it to low if you have higher capacitance, right? Because you need to add more or take away more charge to change the voltage. So basically, it slows down your circuit if you have these large capacitances. So it's always nice, it's always desirable to minimize capacitance, small signal capacitance in your integrated circuit devices. So on this slide is just qualitatively, what are different ways we can use to, let's say, minimize depletion capacitance. A lot of times in a transistor, actually we care more about depletion capacitance rather than diffusion capacitance, at least a MOSFET. BJTs, we do care about diffusion capacitance as well. But in a MOSFET, the PN junctions are usually reverse biased, so the predominant capacitance is the depletion capacitance. So what are 3 ways that we can reduce the junction capacitance? Just looking at, there's only 3, there's like 3 things there. All right. Well, okay, besides area, okay. Reduce the depletion width. That's good. So how do we reduce the depletion width? You can't just go in there and draw. So what are ways to practically that we can, the ways we can fabricate the diode to increase the depletion width? Yeah, so lower dopant concentration. That's good. So basically, you want lower dopant concentration on the lightly doped side, right? So usually one side is heavily doped. You need it to be heavily doped, like for the source and drain regions, to conduct current. Okay, that's good. What's another way? Okay, sorry. One of the 3 ways is to reduce the junction area. So that's what happens when we miniaturize the transistor. We miniaturize the source and drain junction areas as well. What's another way? Maybe by applying a bias. If we can apply a voltage to your PN junction diode, what voltage? What kind of bias, forward or reverse, would you like to apply? Reverse. Very good. So you can apply a reverse bias. And we'll come back to this in a few weeks when we talk about transistors, because that is one thing that we do to a transistor. We can apply a reverse bias to the body region to reduce this junction capacitance. Okay, good. All right, so let's see. I did this for the Schottky diode, but let's review it again. So that if we measure, we can actually electrically measure the junction capacitance. So I'll just sketch it one more time very quickly. It's just the exact same setup as before, but we can hook up a diode like this and say apply different values of VA and apply a really small signal here, so maybe on the order of like 10 millivolt kind of a amplitude signal here. So we can apply a small AC signal on top of a DC bias that we are changing, okay? And then we can use some instrumentation to measure the average displacement current. Okay. Oh yeah, so VA is going to be like negative here for reverse bias. Okay, so this is reverse bias. And okay, so if the current, so the current here is just going to be equal to the junction capacitance, small signal junction capacitance times the rate at which that small signal voltage is changing. Okay, so it has to be, this only works for reverse bias, so you have very small DC current flowing. Okay, because you're going to use this equation to figure out what the junction capacitance is. If there's just current flowing due to the diode, then you're not going to accurately calculate the junction capacitance. Okay. Okay, so if we plug in an equation for a one-sided PN junction for W, then we can come up with this equation. And so remember, this is the dopant concentration on the more lightly doped side. Plot, you can tell hopefully by looking at this equation. So again, we make the measurements only under reverse bias, so that's where VA is negative. So basically we apply different negative values of VA and a small signal voltage on top of that. And from the measured current, we can deduce what C sub j is, and then so we plot 1 over C squared. Okay, so these are from measured data. So the slope is going to be proportional to n. And you can extrapolate. So here we extrapolate the measured data. And so these are measured, and on the right is extrapolated. So you can find the x-intercept, and that will give you the built-in potential. Okay, so you can actually use this approach to figure out or to estimate what your dopant concentration is on the more lightly doped side. Okay, so you have n is determined from the slope, and then VBI is determined from the x-intercept. And then this way you can get the dopant concentration on the more heavily doped side. You have a formula for VBI based on the dopant concentrations on both sides, right? So if you have the dopant concentration on one side and you have VBI, you should be able to figure out the dopant concentration on the other side. So this is a very simple example of I'm just giving you the slope and the intercept values. Okay, so slope and intercept. So you probably can look through this later on your own. But basically, I guess in principle, you should be able to do simple calculations like this. But yeah, this looks a little scary. But anyway, if I give you the slope and the area, you should be able to then calculate the dopant concentration on the more lightly doped side. And from the intercept, you have okay, so this is the formula, the dopant concentration on the more highly doped side and the lightly doped side. This formula is assuming what? It's assuming something. Exactly, that both sides are non-degenerately doped. So non-degenerately, this is a simple example. From a capacitance versus voltage measurement, you can actually determine or estimate the dopant concentrations on both sides of the junction. And yeah, that's it. Okay, so this is a summary of the small signal model. It's just the capacitance in parallel with the conductance. In reality, you also have some series resistance. So last time, remember we talked about what happens at very high levels of current. So if this term only becomes significant, well, yeah, it's usually small. But if you're operating at a very high level of current, remember the conductance is really high. In other words, and then 1 over the conductance is low, at high IDC. So if you're operating at very high bias currents, then this term might be not negligible at high IDC, right? The impact of the series resistance of the quasi-neutral regions is going to be significant if you have tons of current flowing through it. So you start to see some significant voltage drop across those regions. Okay, any questions about the small signal model? So remember, it's only valid to predict changes in current for small changes in voltage. Okay. Okay. So the final thing is, okay, so the small signal model is something that we like to use if we're trying to pass like time varying signal through the diode, okay? Or like to amplify it or something. Okay, the transient response is of interest if you're interested to use the diode not as an amplifier but as a switch, like in the Wheatstone bridge kind of a configuration to a DC, AC to DC voltage converter. Okay, so this is the last part of the lectures. Basically, okay, how does the charge stored in the diode, how does it change if you suddenly want to turn it on or suddenly want to turn it off? So it turns out it's a little bit more complicated to look at the picture of turning off. So we'll look at that first. So this is a plot intended to be sort of linear scale, showing the charge in the stored in the minority carrier charge stored in the quasi-neutral regions. Okay, on the p side on the left, and on the right it's n side. Okay, so under forward bias, you have exponentially enhanced carrier concentrations at the edges of the depletion region, and the carrier concentrations die out as you go deeper and deeper into the quasi-neutral region. Now, under reverse bias, you have almost zero excess minority carrier charge at the edges of the depletion region, and so basically you have a little bit of concentration gradient from the equilibrium value down to 0. Okay, so these are actually p on the n side as a function of x. This is n on the p side as a function of x. So this is not excess carrier concentration. It's showing the real minority carrier concentration. So basically, in order to switch between like a diode in the on state, forward bias, and a diode in the off state, conducting very little current under reverse bias, you have to be able to somehow add or take away those excess minority carriers. So basically, transient response is just telling us, is qualitatively we're going to look at, okay, how does charge get added and how does charge get taken away or killed in order to switch a diode between those two states. And because because it takes time to add charge and takes time to remove charge, there's always going to be a delay. So when you change the applied bias, it's going to take some time for the diode current to actually catch up and reach the final DC value. Okay. Let's look at the turn off transient. So to turn the diode off, we need to remove the carriers. And it turns out, okay, that the time it takes to turn off a diode really depends on the circuit. Okay, so here's a very simple example of a circuit that can be used to switch a diode between forward bias and reverse bias. And it depends on the circuit because it's the circuit that will supply the current, right? If you need to turn off a diode, you need to be able to flow current out of the diode. And then the circuit itself to which the diode is connected is going to limit, is going to set the current that's flowing to turn off the diode. Okay, so in this particular example, we're switching from forward bias. Okay, we start out at before time is 0. Okay, so t negative, the diode is on, flowing some forward bias current. Okay, so looking at this circuit on the left, let's just assume that IF is approximately equal to VF over RF. Okay, so in this particular circuit, let's just assume that the voltage dropped across, there's going to be some voltage across the diode. But let's just say the voltage across the diode is negligible compared to VF. So the current flowing through RF is IF. And for time t is less than 0, this IF is just flowing through the diode like this. Okay? But then at t equals 0, we flip the switch and suddenly apply a reverse bias. Okay? And let's assume then that current that the circuit dictates to flow through the diode is minus IR. And let's just assume it's that the voltage, again, the voltage across the diode is negligible compared to VR. So then we can have, okay, in the off state, we can have current flowing this way, okay, for t greater than 0. Okay, so this The red was for t less than 0. Okay, does that make sense? Okay, so what happens is that the diode, when you first turn it off, is going to conduct negative current dictated by the circuit. But at some point, the current will drop to be equal to what? What is this value of final value of current? Saturation current. Very good. All right. The key here is that there's going to be some delay before the diode actually reaches that small negative reverse bias current. And this negative current that flows is responsible for moving. So let's just draw p-n junction again. So negative current means that holes are leaving this side, electrons are leaving that side, right? So you have now it's some negative voltage here, right? So if you have negative voltage, holes that are positively charged will want to go to the left, and electrons will want to go to the right. Okay, but what carriers are stored on the right? Holes, right? So you have holes here stored, and on the p side you have electrons stored on this side. So what does that mean? That means that the excess minority carriers have to flow across the junction. Right? So the carriers that are stored in the quasi-neutral regions actually have to flow back across the junction from where they came to flow out. Okay, they're not going like that, but anyway, you know what I'm saying? Okay, so that's the key. The excess minority carriers are flowing back across the junction. Okay, so if you look at at time t equals 0, it looks like an exponentially decaying function. But soon after, once you flip the switch, notice the slope has changed direction. Right? So the slope here at the edge of the depletion region is such that the carriers, the excess holes, are going to diffuse to the left, right? Because they're moving back to the p side to flow out of the circuit. I mean, out of the diode through the circuit. Okay? So note that the slope of Pn dx is less than 0. Oh, sorry, is greater than 0. So that holes are diffusing out of the. Okay, so holes leave the quasi-neutral region to the left. What's another way to eliminate holes in the quasi-neutral region? They can diffuse away, or this is another way. They can recombine. They can die. They can die out. So that's what's shown here. That's why so the concentration of holes is slowly dying out with time because you're losing them to the left, but also because they're recombining with majority carrier electrons over time. Okay? And so we can actually, let's see. Okay, so this is the diffusion current. Okay, so we're just taking the diffusion equation, the diffusion current equation, and just pointing out that it's greater than 0. Okay, so what happens then is that eventually the concentration of excess minority carriers reaches 0 at some storage delay time. So this is the storage delay time. So once that happens, then after that, this curve will sort of flatten out a little bit more. So the slope starts to decrease, so the current in magnitude starts to decrease. Okay, so this is where the applied bias, the storage delay time corresponds to the point where the voltage across the junction, applied voltage across the junction is 0, right? Because the excess, this is the excess carrier concentration goes to 0, right? So if the excess carrier concentration goes to 0 at the edge of the depletion region, that means that corresponds to 0 applied bias across the junction. Okay, so qualitatively, that's how a diode turns off. So to derive a simple expression for the storage delay time, we start with the charge control model. And note that for time t greater than 0, so when the switch is switched, so that you have this, you're forcing this minus IR flowing through the diode, you actually can estimate the storage delay time. This is actually a very crude estimation, but qualitatively it makes sense that the amount of time it takes to to remove charge or to have charge die out in the quasi-neutral regions, it's going to be proportional to the minority carrier recombination lifetime. And it's going to be more weakly dependent on the forward current. Okay, so if you have more forward current, that means you have more charge stored, right? You have more charge stored to begin with, so it takes longer to remove it. If you have larger reverse current, that means you're removing charge more quickly, right? So qualitatively, hopefully this equation makes sense. So next time, so why don't you think about, and we'll start at the beginning of class next week, what will happen if we increase the forward current? What will happen if we increase the reverse current? What happens when we change the minority carrier lifetime? How would these transient response curves change? Okay? All right, thanks and have a good weekend. For those of you who didn't pick up the quizzes, feel free to come up.